Hello everybody, here we are with week 14. Woohoo! That means that all we have is this week's worth of new material, and then we're going to say week 15 ends review, and then start finals if you want to take the final early, and then week 16 is the final exam, and we are all done with this semester. I can't believe it. It's so exciting. So, we just have a tiny bit of material left, actually, just a couple of topics. I think we're going to get it done pretty quickly, so let's talk about it. The first little bit that we want to talk about is sets and group theory. That's what it's going to be called. Sets and group theory. And what we're doing here is we're going to talk about certain properties. And what I tell students whenever I do, say, a review for the Texas exam is that a lot of the time where students mess things up on the Texas exam, it's not because you don't know your math. It's because a lot of times you don't know the names of properties or the names of sets or groups or this or that. So we're going to talk and make sure that everybody has the right vocabulary going and all of that. And you know what different number sets are and things to that effect. It may seem pretty elementary, and I know that most of you already have this in your background somewhere. But don't discount it, because I'm telling you, this is where a lot of the mistakes come in the Texas exam, and a lot of times it's because it's just kind of buried in our minds, and we need to dig it back up and make sure we can do it. So first thing we're going to do is talk about number groups, or I'll say number sets, because we're going to use the word group as an actual definition in a little bit, maybe on day 2. But first we're going to talk about number sets. So I often start by saying, whenever I'm working with students on Texas Review, what is the first set of numbers that we normally teach to students? And a lot of times they'll say, well, they first learn how to count, right? So the counting numbers is where they start. So what does that look like? Counting numbers. Like if they were counting on their fingers and their toes, or if they were counting toys, or if they were counting, I don't know, pieces of candy, something like that, they would normally start with 1, 2, 3, 4, right? That kind of thing. So whenever we talk about that, that's just kind of the way things naturally happen with students, with kids, is that they start counting fingers and toes. So there's no fractions in there, there's no decimals, we haven't corrupted them with 0 yet. So there's nothing like that going on for them. So that's very, very normal, and it's very natural. So in math, we call those the natural numbers. The natural numbers, that's what it's called. And there's going to be a letter to denote that. It's a capital N. So you'll see that as you work through some of the problems. And basically, it's just all of the positive whole numbers, okay? So things that we would naturally count. Positive whole numbers is a way to think about it. Although some people say, oh, but I don't know what a whole number is yet. So then you would say no fractions or decimals, no zeros. A lot of times we might talk about things that we don't want to cut up. So entire objects. Because where we get the fractions and the decimals is when we start cutting things up, right? So entire objects, so that would be, like I said, candy, marbles, fingers, we don't want to cut those up, right? So stuff like that, an entire kid, an entire car, I don't know, just anything that we don't want to split up for whatever purpose. So those are things we would count using natural numbers, okay? So that's the first set of things that we would, or number set that we would look at. Next comes, so that's the first one. Next comes whole numbers. And a lot of times I'll tell people, well, think of that like the word HOLE, but they just add the W. So the letter that mathematicians use to denote that is the W. And again, this is no decimals, no fractions, same as above. Nope, no decimals, fractions, etc. It includes all natural numbers. But it also includes 0. So I tell people it's the wrong hole. HOLE is the hole I would dig in the ground, right? But think about that circular thing that I would dig in the ground. I'm going to add that into my natural numbers that I already have up here. So think about it like that, or, you know, think about the fact that, I don't know, what do we do with kids? At some point, they're going to have to learn, okay, we counted first, and now what's the concept of 0? So I had 5 pieces of candy. Susie took all 5 pieces of candy. Now I have no pieces of candy. So me and Susie took all my candy, and I'm left with 0. So that's kind of where they are whenever they learn that concept. If you'll notice, whenever I did the set of numbers up here, 1, 2, 3, 4, I did ... right? That means on until infinity, right? So, like if I was doing set notation up here, it would go on till infinity, or you would just put the ... and not end it, right? So that's what that means whenever I just put ... here, is it goes on till infinity. It doesn't stop at 8 or 9 or 10 or whatever, 11, 12, all of those are in there. So what do we think about a set notation for these, the whole numbers? I think it should go 0, 1, 2, 3, ... Because where these little curly Q brackets just mean the set of, right? But that's because 0 is the smallest, so I will try normally to start at the smallest and move our way up. So we still don't have any negatives in there, but they're coming, okay? And that is actually the next set of my integers. So next is integers. The letter we use for that is I. Okay. And basically, it's all of those positive whole numbers plus their negatives. All of the positive whole numbers plus their negatives. So that's the next set. And it will look like, because we start way down here, well, where would if I have a positive infinity up here, then what would I have on the bottom end? Well, I'd have a negative infinity, right? So I need to start way down there at negative infinity, and so that's going to be represented with, okay, we're going infinitely small here, and then I'll say, okay, start at like -4, -3, -2, -1. See how I'm working my way up the scale? 0's right there, and then I go from negative to 0 to the positives, right? So 1, 2, 3, 4, and then the ... So that if I looked right here, I just have all of my whole numbers. If I looked right there, I just have all of my natural numbers. So now I'm in integers, and I have all of these negatives as well. But again, these are all still whole increments, right? So I have -2, -3, -4. So that's like I lost 4 whole dollars. It's not like I lost $2.75. So still no decimals, still no fractions yet, but we start learning that as we go along. So maybe this would be the situation where I had 5 pieces of candy, and then Susie says, hey, you owe me 7. So I give her my 5, and now I'm -2, right? I owe her 2. Or in the bank, right? I have $4, but I want something that costs $10. Well, how much short am I? I'm short $6, right? So that's a negative in my bank account. Those kinds of things happen. Okay? So in the natural progression, now we've got whole numbers, we've got zeros, we've got negatives. So what comes next for kids? Okay, so hopefully you're thinking about what kids would do. And in my brain, I'm thinking, okay, well, the next thing is, all right, I had a piece of candy. Now maybe I have a candy bar. So what's going to happen with my candy bar? I might want to cut it in half because I might want to share with Susie, right? Or what if I had a pizza? Maybe I want to cut that pizza into 8 pieces or something to that effect. So next up is going to come rational numbers, which normally, whenever I teach that to a lower level class, I would say, see this word ratio in there? What do you think about ratio? Ratio normally means fraction, right? So that's something that we keep in mind is, okay, we've got that fraction running around. Ratios are going to include anything that can be expressed as a fraction. So interestingly, the letter for ratio, rational numbers, is Q. It's going to be because R is already taken. So we'll see that in a minute. But the R is already taken. And if you're thinking about how you would define that, it's any number that can be, it's important that we say it can be expressed as a fraction. So interestingly, let's start with the numbers we already have. We already have, for instance, positive 3 and negative 4. Those were integers, right? So let's talk about an example. 3. Well, we know 3 is a counting number, so it was a natural number. 3 is a whole number because it's inside right here, inside of all the natural numbers plus 0. 3 is an integer because it was a whole number. And 3 is also a fraction because I could write 3 over 1, right? And that means something to me. It's not without meaning. So 3 over 1 totally works, okay? Well, what about negative 4? Same thing, negative 4 over 1, right? What about negative 1/2? Or negative 6/3? Well, that's the same thing, right? So those are definitely ratios or fractions. No worries there. What about the number 1.75? That's a decimal, you may say, right? Well, it is definitely a decimal, but interestingly, it's a terminating decimal. Right? Terminating decimal. And when that happens, we know we could always say, well, what position did it terminate in? That 5 is in the hundredths position, right? So this is 1 75 hundredths, or 1 3/4, right? We know that. So that one is still a fraction, even though it was written as a decimal because it was a terminating decimal. Okay, so then we might say, well, what kinds of decimals are out there? Well, there's definitely terminating decimals, and those can be written as fractions. Still a little spot right here. There's also non-terminating decimals, right? So what's an example of that? The most common one I hear here is 1/3. 1/3 is 0.333, ... I'm on a different podium tonight, and it's a little bit shaky. It's a little weird to me. So 333, let me try that one again. Okay. So this particular guy is not a terminating decimal, but it's definitely a repeating decimal, right? Repeating decimal. So it's important that we know that whenever we're looking at rational numbers, any decimal, so here let's add this in right here, any decimal that either terminates or repeats can be written as a fraction. And in fact, in our 350, 351 classes, or 1350, 1351 classes, here in Commerce, we actually go through that whole entire process for how you would do that and what it would look like to take something, like I just did this terminating guy, that was easy, right? But this non-terminating guy, he can be kind of complicated. So there's an entire process for how that works. So if you're not sure how that works, maybe go look up how to make a repeating decimal look like a fraction, because there's a process for that. So anything that looks like that is a rational number, okay? Now the interesting thing is you didn't hear me say a decimal that is non-terminating, non-repeating, right? So that's the only kind of decimal I haven't talked about, non-terminating, non-repeating, and those are not in here. So there are decimals that are not part of the rational group, and we're going to talk about those. That's my next set. So they're not in there. They're not in that set of numbers. So if something's not rational, then it must be irrational, right? Irrational. Which mathematicians use the notation IR for that. Okay. So this would be numbers that can be expressed as decimals, but not as a fraction. Not as fractions. Okay, so there's some really popular irrational numbers, and I bet if I asked you right now, what's an irrational number? A number that does not repeat and does not terminate, okay, which would make it not written as a fraction, not repeating, not terminating. I bet a lot of you would say, oh, I'm thinking of, yep, pi. He's very common, very popular for people. I did a review session last month on this, and sure enough, first one mentioned was pi. The next one mentioned a lot of times, because we know pi is 3.1415926, blah, 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 right? Okay, so he's pretty common. The next one a lot of time is e. If you don't remember e, you used him probably when you were doing continuous compounding in that formula a equals pe to the rt. He's used in logarithms, natural log, log base e, that kind of stuff. So he's kind of floats around. He's called the natural number a lot of times, and he's like 2.72. He rounds to 2.72, but he's got a long non-terminating decimal also. So e is in that group. But then there are a whole bunch of things that people don't necessarily think about whenever they're doing these. So I tell people all the time, you know these, you just don't necessarily know that they're irrational. So for instance, there's a huge group of radicals, okay? So square root of, for instance, I'll do squares, but you could do fourth roots and stuff like that. If I put a 4 in here, square root of 4, what would you think about that? Hopefully you think square root of 4 is 2, and 2, we already know 2, right? 2 was way up here in the natural numbers. So he's a natural number, he's a whole number, 2 is an integer, 2 can be written as a fraction. So 2 is not going to be irrational, right? So we don't want things square root of 4 because we can actually take that radical and simplify it and make it a whole number. But what about the square root of 5? What do we think about that guy? Well, the square root of 5 is somewhere between the square root of 4 and the square root of 9. Well, we know the square root of 4 is 2. We know the square root of 9 is 3. That comes back to perfect squares, which we did like first week of school, right? So if something is a perfect square and I take the square root of it, like 4, 9, square root of 81, square root of 100, all those are doable. But these guys are what? Not perfect squares. So square root of 5, square root of 3. They don't have to be prime numbers, so square root of 6. Even though 6 is not prime, it's a composite number, he's still between, this number right here is still between square root of 4 and square root of 9. So it's still going to be like 2 point something something, right? You could do like square root of 12. That's not a perfect square. So when I take that, if you punch that into your calculator, the square root of 12, you are not going to get a whole number. It's going to be like 3 point blah, 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 blah. Okay. You could pick really crazy numbers like square root of, I don't know, 42, right? It doesn't matter. It's not a perfect square. 49 would. Square root of 49 would be 7, but square root of 42 is not. So there's a whole list of those. And by the way, at any time, I could throw a negative out in front of one of these radicals. So the negative square root of 42, well, this is going to be, well, let me not pick that one. Let me do one I can do in my head. What is that? That's between, now I'm stuck on it. Square root of 42 is between square root of 36, which would be 6, and square root of 49, which would be 7. So this is 6 point something, right? So this is negative 6 point something. And I could do the same out here in front of the square root of 6. Negative square root of 6, well, that would be negative 2 point something. So I can throw negatives on the outside of the radical all day long. It doesn't work if I had done the square root of, say, negative 6, because the negative on the inside there would give me something that we call I, right? It would kick me out. So I would have a square root of a negative number, which would be a problem. It also doesn't work if I have a cubed root of negative 6, because a cubed root of negative 6 you can actually take. It would be some horrendous number. But negative times a negative times a negative in here, we can do it. So if it was cubed root, I could do it. But if it was the fourth root, like the fourth root of 2, for instance, that guy counts in there. Or fourth root of 2. Yeah, he counts in there. So you have to be kind of careful which roots work and which roots don't work here to throw me into irrational numbers. Okay, but the cubed root of 7, let me throw it up here. Cubed root of 7, yeah, that's not something that I can take a root of. If it was cubed root of 8, I could. But I can't take the cubed root of 7, and so that automatically throws me into irrational numbers. Okay? So irrational numbers, and then what comes next? Well, I got to stick all of these things together somehow, right? So that's a set of numbers. Did I get them all? Yeah. That's a set of numbers. So next comes put all the numbers together, basically, right? And that's when the real number line comes in. Real numbers. That's the one that gets the letter R for his notation. And this is any positive or negative number large or small, small, fraction, decimal, etc. Or 0. Throw him in there too, right? Because basically when you think real numbers, you should think what goes on a real number line. 0's in the middle, 1's out here, 2's out here, 3's out here, 4's out here, -1, -2, and so on. But also in here, like I could put a point right here on my number line and say, that represents pi. Now I know it's not exactly pi, right? But it represents pi. If I know that the negative square root of 6 is about negative 2 point something, then I can put a point out here somewhere and say that that's about the negative square root of 6 right there. So I can give him a place on that real number line. So anything that can be shown on the real number line, well, that's a real number. So it's all the stuff we've talked about so far, right? It's all encompassing. So that's kind of the way that works for me. Then we go, well, then what the heck's not on there? Well, what I said earlier, right? The imaginary numbers. So imaginary numbers are not on the real number line because they're imaginary, right? So they can't go on the real number line. So you don't get to go play in the party. Sorry, guys. Okay. So then we have to have another set of numbers because we got to talk about those guys that didn't get to come to the real number line party. You're not invited to the real number line party. You have to have your own party. Okay, so fine. Let's talk about imaginary numbers, which are going to be part of the complex numbers. Okay, and generally we call those the group of C, complex. And this is numbers that can be written in A plus BI form is what they call it, where A is a real part and BI is the imaginary part. Okay, so what that means is that the complex part of it is that it has a real portion right here in A. It has an imaginary portion right here in BI. So it's got a little bit of everything, so that makes it complicated or complex is what they call it. Okay, so the fact that I have both portions in there automatically should kick me out of just real, right? Because I've got this added part. Now the interesting thing though is, well, let's get some examples in here. So example. Well, we all know stuff like 2i, right? Square root of negative 4 is 2i. Okay, stuff like negative 5i. Okay, that's fine. And then if it's in the, because those are both imaginary parts, right? If it's in the A plus BI format, then it could be something like 6 minus 4i, right? Because, well, let's make it a plus 4i, but also 6 minus 4i, because here's the plus part. Here would be the plus a negative part, right? Plus a negative 4, or just the fact that we know that addition and subtraction are opposite operations. A lot of times we just write it as a plus bi there, but we know that includes plus where b is a negative integer basically here, right? We could put in a plus a negative 4. So we'll count that as the same kind of stuff. Also complex, right? Because you could have said this. This is what I'm saying. 6 plus negative 4i. Those are the same thing right there. That's the word or. Okay. Those are the same thing, or they're equivalent statements, we should say. So they represent the same stuff, so we can count both of those. And they are in the complex. But the weirdness is, nobody ever cares that I just say 2i. However, that's not quite in that format, is it? That's just the imaginary part. So what's going on here with the A? Because it's supposed to have an A plus BI format. It only has the BI there, right? What's really happening is we have 0 plus 2i. Does everybody agree with that? That's equivalent to 2i. Okay. Well, if that's the case, then what is this? That is my A being 0, but 0 is a real number, right? Part of the real number set. So I can do that. And basically, eventually we just say, as mathematicians, we're really lazy. We don't always want to write that. We'll just not write it. Okay? So this one is the same as 0 minus 5i. Is that okay? Where the real number part there is a 0. All right? So let's be a little bit more tricky about this, so to speak. What about something that has a real number part, but not an imaginary part? Can we count that? So can I count 5? If I wanted it to look like this format, A plus BI, what would that have to be? 5 plus 0i. Is that in the right format? Is it okay for B to be a 0? Yeah, we didn't say it couldn't be, right? Okay. What about 1/3? Well, 1/3 would be what? 1/3 plus 0i. Or you could say minus 0i. That would work too. It wouldn't matter because 0 is neither positive nor negative, so it doesn't matter if we put a plus or a minus there. Okay, so that could work out. 1/3 plus 0i. And now what? We don't care about that either, do we? So what that means is that complex numbers, while they incorporate these things, the A plus BI formatting, they also include whole numbers. 5 was a whole number. Fraction numbers, right? Could I write pi plus 2i? Absolutely, right? You might see something like that in a pre-calculus course or in a calculus course. So absolutely that'll count. So all of these things end up being complex numbers. So what does that tell me? It says to me that anything, let's put it this way, complex numbers encompass all real numbers plus imaginary numbers. Okay, so then this is the way that kids think, right? That kids learn. We start them out. Let me go back. Count, 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 count. Okay, what happens if you lose all your marbles? Okay, what happens if you owe me $5? Okay, what happens if I want to cut that pizza into portions or slice up that pie or take my candy bar and cut it in half? Fractions. Okay, what happens if something can't be written as a fraction, if it's an irrational number? Oh, now we have the real number system, and this is by about middle school. They have the real number line, right, for sure. They've already seen some square root of 5 stuff. And then last but not least, and this would be a high school topic, well, maybe 8th grade, if you had an algebra class in 8th grade, they might see some I's. Complex numbers, right? So that's where we start pushing things on them a little bit, and this is where a lot of students start losing stuff, right? Because they're like, what do you mean a number is imaginary? How can a number possibly be an imaginary number? And the answer is, basically, mathematicians had this I stuff, and they had a square root of a -4, right? That's how we get I. They had the square root of a negative number, and we couldn't figure out what times itself gives me a negative number inside of the radical. So we said, hey, we can't deal with that. It doesn't compute in our head. I want to do something with that. I don't want to just leave it like that. I want to be able to do stuff and work with stuff. So what can we do? And some genius, if you in my math history class, you'll learn all about it, figured out, hey, let's call it I. Let's give it a value and make it imaginary. So that works, right? We can do it, we can use it. So that's what ends up happening for us is at some point near upper middle school or high school, we throw these complex numbers at students, we throw in I, and a lot of times that kind of breaks them down. They're normally pretty good with fractions. It's rough with operations on fractions, but they understand how to cut a candy bar in half or thirds or whatever. Irrational numbers throw them a little bit, and then complex numbers a lot. So you might have a question that was something like, just classify this number. How would you classify? That's my question. How would you classify -7? In fact, I think this might actually be your participation question for the day. So how would you classify -7? And of course the answer is what? Well, go through your entire list. Is -7 a natural number? Do we naturally count with negatives? No. Is it a whole number? No. But it's an integer, right? So start there. It's an integer. Okay. But that's not all, right? Is it also a rational number? Can I write it as a fraction? Yep, -7/1, right? So it's a rational number. Okay, what else is it? Well, is it an irrational? No, because rational, irrational is a dichotomy, right? You are either in the rational group or the irrational group. You cannot be in both at the same time. So ir, that prefix, literally means not. So these are not rational. So if you're rational, then you can't be in the not rational. So it is not irrational, but what about the next group? Real numbers. Is -7 on that number line? Yes, it is. So it's part of the real numbers. And then could it be written in a plus bi format? Absolutely, but the b would be a 0, right? -7 plus 0i. But it could still be in there, so it's still part of the complex numbers. Okay, so one particular number, -7 in this case, is in 4 different sets. So absolutely we can have it in lots of different sets. So that brings up the question, well, what does that mean? What does it look like? And I really like to do this with my students in the 1350 and 1351 group. So what I'll do is we'll start out with the first group, which is natural numbers, and I stick it right here in the middle. Okay, natural numbers is my building block. That's my counting numbers, 1, 2, 3, right? And then around that, including that, but also adding the 0 is whole numbers. Okay, that's not bad. So anything that's a natural number, also a whole number. Around that, including the whole numbers, and then adding to the whole numbers is integers, and what do we add to it? We add the negatives, right? So integers, I, that was I. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah. Then we add 0, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah. And then integers, well, now we're adding in -1, -2, -3, okay? Then what? Then comes the rational numbers. So, hey, they include all of those things. We can take anything that's an integer, anything that's a whole number. We can write all of these as fractions. And we'll also add stuff like 2/3 or -5/4. Oh, that's an interesting one because it's bigger than 1, right? -5/4. So it's still a rational number because it's still a fraction, right? Even though it would really be a mixed number if I kind of simplified that, right? Okay, so there's my rational numbers, and then what? Stinking irrational numbers. Those don't include any of these, because if all of these things are rational, there's one set of my dichotomy. Then over here in its own little group, own little group has to be irrational, right? Okay, so you guys are my irrational. You're kind of off by yourself. But then don't worry, we're going to bring them back into the group because then we're going to have something that encompasses all of these things, right? And those are the real numbers. Okay. Some people, by the way, would put another little circle out here and put IM for imaginary, and that would be fine. So let me just do that because they are kind of their own little subgroup. We didn't call them their own group, their own set, but they are kind of their own little subset there. So imaginaries are here, and then there will be one gigantic circle all the way around. All the real numbers plus the imaginaries equals complex numbers, right? So those are my two, my really big set there is complex. It includes everything, but don't forget that imaginary can be their own little set, but often we just don't even put that there and we just call it complex. So whichever you prefer is fine. All right, so all of that to say, hey, those are all my sets. You didn't even know you had that many number sets, did you? Okay, so this is a Venn diagram representation of all of our number sets. Yay, so you gotta know those are out there. What I see on the Texas exam is that there will be a question that says, hey, you got a group of natural numbers, blah, 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 and people get stuck there because they're like, what the heck's a natural number? So if you can kind of visualize this, starting with, they call this a nested Venn diagram, right? This set is inside of this set is inside of that. Kind of like the little Russian dolls that you get whenever you go on an Alaskan cruise. You can pick up those little nesting dolls, right? So that's what they're called, is nesting sets. And so one is inside of the other is inside of the other. So if you can kind of keep something like that in your brain, then maybe it helps you whenever you see a question that says, okay, what about the natural numbers, or what about integers? So if you can keep in mind what is an integer, it will help you. All right? Okay, so then what? Okay, we have all of our number sets, and then what the heck are we going to do with them? So we need some algebraic properties. Algebraic properties. And again, a lot of times I think people know these algebraic properties. However, they just think, oh, I don't remember those. I don't remember what that property means. Or maybe I know the word for the property, but I don't remember the definition for the property. So just a quick review. Remember, they're all out there, algebraic properties. Interesting thing, whenever you're using about algebraic properties, they use an operation and a set. Okay, an operation and a set. So the set part, we just talked about all the different number sets, so that's what we're talking about there. But whenever we're talking about an operation, what operations are we talking about? Operations in general are add, subtract, multiply, and divide, right? Okay, there's other operations like square root and stuff like that, but normally when we're talking about operations, we normally are talking about add, subtract, multiply, divide. Okay, so some of the properties that you probably already know. All right, how about associative property? Okay, so hopefully in your brain you're thinking, I at least know that word, right? You've at least seen the associative property before. But I find that a lot of times people get these mixed up. So the question becomes, all right, you've got the associative property. Which one is it? Can you tell me right now what the associative property tells you? If you can't come up with it pretty stinking quickly, then you probably need a review. So that's what we're doing. Okay. So most of these properties start out with given a set and an operation. Okay, so it's almost always given these things. We're going to start out. We know what set of numbers we're talking about, and we know what operation we want to do. So it says if three elements of that set are grouped in different manners the outcome is still the same. That's the definition of the associative property. Given a set and an operation, if you have three elements that are in that set and they are grouped in different manners, then the outcome is still the same. It doesn't matter. Okay, so and here's the notation for that. So first of all, let's talk about this word elements. Elements means something that is inside of that group. So for instance, some elements of integers could be -5, +3, 0. Those are all elements of that group, right? Of that set, of that set. So you start looking at it and you say, here's the example. And I'm not always going to be really explicit like this, but they say A, and this notation means operation. A with the operation, whatever operation it is. B, those are in parentheses. And then we do the operation again, and we get C is equal to A operation B operation C. And this time we move the parentheses. So you'll notice the grouping, we're saying they're grouped in different manners. So move the grouping from A and B to B and C. So we're grouping them differently, right? So the operation there looks a little unusual, so let's put it in terms we know, right? So how about operations we know? So A plus B plus C is the same as A plus B plus C. Is that true or false? Okay, well, it might depend on what set we're in. It might depend on what operation we're doing. So in this case, I'm doing addition, and let's say we're looking at whole numbers, addition of whole numbers. So the question that you'll end up seeing is something like this. Is addition, that's my operation, associative on the set of whole numbers? Okay, is addition associative on the set of whole numbers? And of course, what are you going to do? You are going to look at it and say, well, I don't know. Let me think about it. I mean, we might actually know this one, but the way we'll check for these properties is to say, let's see. And in general, what I would say is you should be looking for what is the counterexample. So what would make this not work? Okay, so for instance, we know, let's just use some numbers here. 3 plus 2 plus 5, and then 3 plus 2 plus 5. Make sure I didn't change the order. It's 3, 2, 5, 3, 2, 5. Those didn't change, but I moved the parentheses. Are those the same? So over here I get a 5 plus 5, I get 10. Is that equal to 3 plus 7? Yeah, that's also 10, right? So those are equivalent statements, so therefore this is equal, so that means that we think, addition is associative on the set of whole numbers. But like I said, you need to kind of think about what would be the one that would throw me out of working. So what's the weirdo in whole numbers, in other words? Well, whole numbers are all of the natural numbers plus 0. So the question becomes, would 0 make this not work, basically? So if I had put a 0 here, 3 plus 0 plus 5, and then it's 3 plus 0 plus 5, does that make this not be equivalent? The answer is no. It actually does not. So, and we can play with different examples and try different things, but what we're going to see here is that addition is associative on the set of whole numbers, so the answer here is actually a yes. Okay, so you're going to see a few things like that. Well, then is multiplication associative on the set of whole numbers? Is subtraction associative on the set of whole numbers? By the way, it may not be. Is division associative on the set of whole numbers? And what you're going to find is that a lot of times addition and multiplication may work, but subtraction and division may not. And it also depends on what sets I'm talking about. A lot of times something may not work with natural numbers, but it might work with integers, or it might not work with whole numbers, but it might work with complex numbers. So you have to be really careful. You can't just say these things always work, because this one, for instance, the associative property does not always work in all sets with all operations. So, and there's just a lot of combinations where we would have to play with them and see. So let me move through the rest of the properties, and then you're going to have some homework that's going to say, okay, what do you know about this? What's going on with these properties? Is this or is it not? And again, always look for the things that might throw you off. 0 a lot of times is a problem. Negative numbers can cause me problems. Subtracting and dividing by things cause problems. So just really kind of look at that and think about it as you go through. Okay, next property. Again, you've probably heard of this before, but you may not remember a definition for it. Commutative property. Property. Commutative property. Okay. All right, commutative property. Oh, I'm sorry. Let me go back just for a minute. When I teach this, let me give you a little reminder. When I teach this, I say, look at associative. What do you think when you're doing that? Associative. I think what's associated together, okay? So when I put the parentheses here, I know this isn't about order. So that's why I made sure that my 3, 2, 5 was still in the same order, 3, 2, 5. Okay, don't move that. But when I'm associating things differently, I think grouping. So associative and grouping go together. Okay, so I'm moving which guys are kind of pushed together in a grouping. So here the A and the B are associated inside of the grouping, but here the B and the C are associated inside of the grouping. So that's what I think whenever I see associative. So that's how I keep that straight in my head, is that associative goes with grouping. And I'll show you associative and grouping. I also have a little bit of an alphabetical order thing. I know that the other one that people mix this up with, and I'll just go ahead and tell you, is commutative property, which is the one I'm about to show you. And that one is order doesn't matter. So we probably already know that, but sometimes we get these two confused. So I like to do an alphabetical thing, if nothing else. A comes before C, associative before commutative. G comes before O, grouping comes before order. So if you're an alphabetical kind of person, maybe that helps. A lot of times I've also told like my intermediate algebra students, A, G, ag, C, O, like company or that kind of thing. So whatever works for you. Just kind of come up with a mnemonic or a way to memorize it. Keep it in your head because you're going to need that to be something you can do. Okay, commutative property says, given a set and an operation, if you have two elements, and it says two elements, but it could be more than two elements, so we'll just start with two elements. If two elements of that set are combined in different ways, or different manners, different orders, the outcome is still the same. The outcome is still the same. So a lot of times we say order doesn't matter, right? The order just doesn't matter which way I do it. And again, a generic of this is, let's use the star operation. Okay, C star D is equal to D star C. So again, all we've changed in this case is the order. So there's no grouping necessarily involved, but the order changed. So let's think about it. Is subtraction commutative? So, question. Is subtraction commutative on the set of, let's stick with whole numbers. We did it a second ago, whole numbers. Okay. So what that means is, can I do C minus D and get the same answer as if I did D minus C? I want to know that. So they're asking, is it? And I want to know, is it yes or no? Okay, so I think we can probably come up with some examples pretty quickly that show me no. If I just use, for instance, the numbers 6 and 7. 6, let's try 7 minus 6. Is that equal to 6 minus 7? So all I did was change the order, same numbers. So we know that this is not true, right? 7 minus 6 is a 1, but 6 minus 7 is a negative 1. That's an absolutely not true thing. So when I say, is subtraction commutative on the set of whole numbers, the answer is no. And I told you, you kind of look out for subtraction and division. Sometimes subtraction and division will have whatever property it is, but a lot of times these things just don't work, right? Okay, so that was commutative. Let me back up, I'm sorry. That was commutative, given a set and operation. Order doesn't matter. And clearly in subtraction with whole numbers, order does matter, right? So it's a big deal there. All right. I'm watching my time on this video, and I feel like I'm about to get killed on this machine, it's not going to let me go much longer because I'm at 54 minutes. So I think I'm actually going to stop it and then start a new video because I still have 1, 2, 3 more operations to go before we're ready to be done with this. So I'm just going to stop, put a peg in it. You guys think, take a break, shake it off, whatever, and we'll come back and do video number 2 from day 1. It won't be that long. I know I can't do it in the next 5 minutes. All right, coming right back.